The space S consists of all infinitely differentiable functions f of t such that no matter how many times you differentiate it and by whatever positive power you multiply it with, it should be bounded. So we have already seen that if you take the hyperbolic cosh at inverse, that's an element in the Schwar space. Classic example is e to the power minus x squared and polynomial times e to the power minus x squared. These are classic examples of elements in the Schwar space. So now let us look at some of the properties of the Schwar space S. Obviously it's a vector space, it's closed under addition and multiplication by scalars. So we have got a vector space structure. It is also an algebra. I can multiply two elements in S and the result is again in S. That's also a very pleasant property of the Schwar space. Next, if you take an element in the Schwar space, by very definition, f prime is also in the Schwar space. If you take an element in the Schwar space and multiply it by a polynomial, then the product is again in the Schwar space. Every element of the Schwar space is absolutely integrable over the whole real line. And so for every element of the Schwar space, the Fourier transform is defined. It's an easy exercise for you to prove these basic properties and I leave it to you to verify them. So now we shall now prove that if f is in the Schwar space, the Fourier transform is also in the Schwar space. So the Schwar space is a vector space, it is an algebra, it's closed under differentiation, it's closed under multiplication by polynomials, it's closed under taking Fourier transforms. It's the most pleasant space to work with. So the Fourier transform maps S into itself as a linear transformation. Now we will also see that it is a surjective from S to S, it's injective from S to S, so it's an isomorphism of the Schwar space. You know an example of an eigenfunction of the Fourier transform. Recall the Fourier transform of the Gaussian. If you recall the formula for the Fourier transform of the Gaussian, you will immediately be able to find an eigenfunction for the Fourier transform operator. There are others, but you have to look at the list of Fourier transforms that you have calculated. So now let's prove theorem 36. Suppose f is in the Schwar space, then f hat is also in the Schwar space. So first write the definition of the Fourier transform. F hat of chi is integral minus infinity to infinity e to the power minus it chi f of t dt. Now differentiate this under the integral sign. So let us differentiate it once. dd chi of f hat of chi. The derivative falls on the exponential factor you get as a result and minus it. The minus I comes out and the t can be clubbed with f of t and you get e to the power minus I chi t into t times f of t. But remember, f is in the Schwar space, so t times f of t is also in the Schwar space. So everything goes through. So the derivative dd chi of f hat of chi is minus I times the Fourier transform of t f t. Now I can differentiate it successively. So the nth derivative of the Fourier transform is minus 1 to the power n into e to the power minus it chi into t to the power n times f of t dt. Remember that t to the power n times f of t is again in the Schwar space. So now let us write the integrand by inserting 1 plus t squared raised to the power minus 1 and 1 plus t squared. So the bracketed term, the term in the brace bracket, e to the power minus it chi, t to the power n f of t, 1 plus t squared. 1 plus t squared into t to the power n is a polynomial. So polynomial multiplied by an element of the Schwar space is again an element of the Schwar space. So quantity under the brace bracket is bounded in absolute value. So now we get the following. Multiply the integral by minus I chi to the power k. So get minus I chi to the power k dd chi to the power n f hat chi equals minus I to the power n integral minus infinity to infinity ddt to the power k into e to the power minus it chi t to the power n f of t dt. Now you keep integrating the parts and using the fact that the kth derivative of t to the power n f of t is again the Schwar space. So we conclude that chi to the power k d to the n f hat of chi is bounded for every pair of integers n and k positive. Since k is arbitrary, The result is proved that the derivative of the Fourier transform multiplied by polynomial is again in the Schwar space. The result is proved. So, if f is in the Schwar space, f hat is also in the Schwar space. Now, there are two basic formulas connecting the Fourier transform and differentiation, connecting the Fourier transform and multiplication by t. If I differentiate the function f of t and then take its Fourier transform, it is the same as first taking the Fourier transform and multiplying by I chi. That's the first formula that you see on theorem 37. The second formula that you see is that first multiply the function f of t by t and take the Fourier transform, you get minus 1 upon I dd chi f hat of chi. In other words, multiplication by it and then Fourier transform is the same as differentiation of the Fourier transform. The exact formula, there is a minus sign floating around and you see that in the displayed formulas. So let's prove these things. To prove the first, you simply have to integrate by parts, and to prove the second, you simply have to differentiate under the integral sign. So let us look at the second one. dd chi of f hat of chi is dd chi integral minus infinity to infinity e to the power minus it chi f of t dt. That is integral minus infinity to infinity minus it e to the power minus it chi f of t dt divided by minus I, and you get the second formula. So that was easy. So now let us look at the Hermits ODEs and Hermit polynomial. So what is the Hermits differential equation? The Hermits differential equation is this ordinary differential equation y double prime minus 2xy prime plus 2 lambda y equal to 0. It's a nice second order ODE. In your undergraduate courses, you have found series solutions of this Hermits differential equation, and you found a very nice generating function, a nice recursion formula for the coefficients, and you solved the Hermits equation as a power series. So now let us transform the Hermits equation by a simple substitution, namely y equal to u e to the power x squared by 2. So what is the differential equation satisfied by u? It is very simple. It is u double prime minus x squared u plus 2 lambda plus 1 u equal to 0. Now look at the combination u double prime minus x squared u. What happens when you take the Fourier transform of u double prime? Let's go back to the previous slides. What happens when you take the Fourier transform of u double prime? You simply have to look at the first formula in this theorem 37 and apply it twice. Again, what happens when you apply Fourier transform to minus x squared u, or if you want a variable to be t, minus t squared ut. If you take the Fourier transform, what are you going to get? Again, go back to the theorem 37 and look at the second formula in theorem 37. Fourier transform of t squared f is going to be minus 1 upon I dd chi applied twice to f hat. So two minuses, that disappears, but you have minus 1 remaining because of the I squared term. So the Fourier transform of t squared f of t is minus second derivative of the Fourier transform, and the Fourier transform of the second derivative of f is going to be chi squared times the Fourier transform of f. So what happens to this combination u double prime minus x squared u when you take the Fourier transform? When you look at this expression u double prime minus x squared u and you take its Fourier transform, you again get the same expression thanks to theorem 37. And so the differential equation, when you take the Fourier transform, you get back the same differential equation. So it means that if u is a solution of this equation, then u hat is also a solution of the same equation. Now, suppose if u is a element in the Schwar space. Suppose that you got a solution of the u equation which lies in the Schwar space, then u hat is also in the Schwar space. So now you got two solutions of the same second order ODE, u double prime minus x squared u plus 2 lambda plus 1 u equal to 0, both in the Schwar space. Can they be linearly independent? Answer is no. The reason is very simple. Go back to your ODE courses and look at the Abel-Liouville formula. If you take two solutions y1 and y2 of a second order ODE, y double prime plus pxy prime plus qxy equal to 0. take two solutions y1 and y2. Let w be the Wronskian. What is the formula for w? W at x equal to w of x naught e to the power minus integral px dx. But in the transformed equation, in the u equation which is in the slide, you see there is no u prime term in the differential equation. So the Wronskian is going to be a constant. The Wronskian of any two solutions is constant. And recall that if two solutions of a second order ODE are linearly independent if and only if the Wronskian is non-zero, but the Wronskian is constant. So now suppose if you have two solutions y and y hat, both of them are in the Schwar space, and if they are linearly independent, then what will happen to the Wronskian? U hat is the first row of the Wronskian, but that first row goes to 0 very rapidly as x goes to infinity. But the Wronskian is constant, so it must be 0. So the Wronskian of u and u hat must be 0, so u and u hat must be linearly dependent. In other words, u hat must be a scalar multiple of u. In other words, u hat and u are multiples of each other. And so, if u is a solution, u hat is also a solution, but u hat is constant times u. In other words, this solution u of the Hermits equation, which lies in the Schwar space, is an eigenfunction of the Fourier transform operator. Y double prime minus 2xy prime plus 2 lambda y has a polynomial solution h and x when lambda is a natural number. So the u function is h and x times e to the power minus x squared by 2. So these polynomials h and x times e to the power minus x squared by 2 is a family of eigenfunctions of the Fourier transform operator. So we have seen that the Fourier transform is a linear transformation from S to itself, and we have listed a bunch of eigenvectors for this linear transformation. Now let us come to the very important theorem, the Fourier inversion theorem, theorem 38. Suppose f is a function in the Schwar space, then the Fourier transform is also in the Schwar space. So I can calculate the Fourier transform again or the Fourier transform. I can take the second Fourier transform. What will happen? So you get the Fourier inversion formula. There is a sign flip that happens. You get f of t equal to 1 upon 2 pi integral minus infinity to infinity f hat of chi e to the power I t chi d chi. Remember, you don't have e to the power minus I t chi, you have e to the power plus I t chi. That's a sign flip that I spoke about. This is the inversion theorem, equation 4.6. To prove this, let us try to prove this by brute force. So we have this integral on the right hand side. Let us try to prove RHS equal to LHS. In the RHS, you got integral minus infinity to infinity f hat of chi e to the power I t chi. Now you want to say that f hat of chi is integral minus infinity to infinity f of x e to the power minus I x chi. And so you get a double integral, a repeated integral rather. And you want to switch the order of integration. You switch the order of integration, then the integral that you get with respect to the chi variable is integral minus infinity to infinity exponential of I times t minus x chi d chi. This integral as it stands is meaningless. So how to circumvent this difficulty? To circumvent this difficulty, we introduce a nice trick called the x minus epsilon x squared trick. So what we do is the following. We write integral minus infinity to infinity f hat of chi e to the power I t chi as limit epsilon goes to 0, integral minus infinity to infinity f hat of chi e to the power I t chi e to the power minus epsilon chi squared d chi. I have introduced an e to the power minus epsilon chi squared in the integral, and I am allowing the epsilon to go to 0. So now let us look at this integral with the epsilon business thrown in. So now let us write the expression for f hat. So we get integral minus infinity to infinity f hat of chi e to the power I t chi d chi is limit as epsilon goes to 0, integral minus infinity to infinity d chi integral minus infinity to infinity f of x e to the power I chi t minus x minus epsilon chi squared dx. Now we can safely invert the order of the integrals and integrate first with respect to chi and then with respect to x. So fx dx comes out as the later integral, and the first integral that you do is with respect to chi, namely integral minus infinity to infinity e to the power I chi times t minus x minus epsilon chi squared d chi. So now this integral with respect to chi is a familiar integral. It is the Fourier transform of the Gaussian that we have just computed in the last lecture. So now let us use the formula for the Fourier transform of the Gaussian that we have computed and let us put it in. So what we get is limit as epsilon goes to 0 root pi by root epsilon integral minus infinity to infinity x of minus x minus t squared upon 4 epsilon fx dx. Now let us make a change of variables x equal to t plus root 4 epsilon s, so that the root epsilon cancels out. Dx is 2 root epsilon ds, and so we are left with a factor of root pi, and we get limit as epsilon goes to 0 integral minus infinity to infinity f of t plus square root of 4 epsilon s e to the power minus s squared ds. Now I take the limit epsilon going to 0 inside the integral, because the function f is the Schwar space and the Schwar space functions are rapidly decreasing. So Lebesgue's dominated convergence theorem is applicable, and I can take the limit inside the integral, and f of t plus root 4 epsilon s simply converges to f of t, and that doesn't depend on s, so f of t comes out and we are left with integral minus infinity to infinity e to the power minus s squared ds, which is root pi. So all in all we get 2 pi f of t, and the proof is complete. Now we shall see a bunch of exercises based on this e to the power minus epsilon x squared trick. First example is, prove that integral minus infinity to infinity f hat chi d chi is 2 pi f of 0. Remember that if f is the Schwar's class, f hat is also in the Schwar's class, and so f hat is integrable function. So what is its integral? So again let us try a brute force argument. Simply put in the formula for f hat. Integral minus infinity to infinity f hat chi d chi is integral minus infinity to infinity d chi into integral minus infinity to infinity f of x e to the power minus I chi x dx. Now try to switch the order of integrals. What do you get? You run into the same difficulty again. The outer integral is fx dx and the inner integral is integral over the real line e to the power minus I chi x d chi, which is meaningless as it stands. So the switching of the orders of integrals is suspect. It is not valid. To circumvent this difficulty, we shall employ the e to the power minus epsilon chi squared trick. So let us start all over again. Integral minus infinity to infinity f hat chi d chi is limit as epsilon goes to 0, integral minus infinity to infinity e to the power minus epsilon chi squared f hat chi d chi. Now put the formula for f hat chi. What is f hat chi? Integral minus infinity to infinity fx e to the power minus I x chi dx. Now you can safely switch the order of integrals. Fx dx comes out as the later integral. The first integral that you need to compute is with respect to chi, namely integral minus infinity to infinity e to the power minus epsilon chi squared minus I x chi d chi. Again we see the Fourier transform of the Gaussian that we have computed, and we'll get as before integral minus infinity to infinity f hat chi d chi is limit as epsilon goes to 0 root pi by root epsilon integral minus infinity to infinity fx e to the power minus x squared by 4 epsilon dx. Put x equal to 2y root epsilon. What do we get? We get dx equal to 2 root epsilon dy. The root epsilon cancels out and we are left with limit as epsilon goes to 0 2 root pi integral minus infinity to infinity f of 2y root epsilon e to the power minus y squared dy. Now it's a matter of taking the limit inside the integral. Appeal to the dominated convergence theorem. F of 2y root epsilon converges to f of 0, and the f of 0 comes out. integral minus infinity to infinity e to the power minus y squared dy is root epsilon. We get 2 pi f of 0 as advertised. Let us look at some more examples. You can try to use this e to the power minus epsilon t squared trick to compute the Fourier transform of sin at by t. You need to be careful. Compute the Fourier transform of f of t equal to 1 upon t squared plus a squared by obtaining a second order ODE for f. Use the exponential of minus epsilon t squared trick to obtain a second order ODE for the function 2 upon pi integral 1 to infinity sin tx dt upon root of t squared minus 1. You will recognize the Bessel's function coming out as a result. You can try to prove the same result using Laplace transforms instead. Call the integral I of x. Call the integral I of x and try to take the Laplace transform of I of x. Get an expression which is in closed form and take the inverse Laplace transform. This is the other alternative. Please try out these exercises and we shall continue this later. This last example has been taken from the book of Hans Weber, which is written in German on the partial differential equations of mathematical physics, first volume. It's based on Riemann's lectures and this formula appears on page 175.